we have Physics Ph.D. qualifying exam practice problem number 31 in quantum mechanics domain. So let's begin. Three-level quantum system has unperturbed Hamiltonian. H naught equals the following matrix: E sub rho 1, E sub 1, 0, 0, rho 2, 0, E sub 2, 0, rho 3, 0, 0, E sub 3. Subjected to the perturbation V of t equals V naught cosine omega t. And then the matrix 0, 1, 0, 1, 0, 1, 0, 1, 0, respectively for the rows. Part A, derive the first order transition amplitudes. Okay, so this is a time-dependent perturbation theory problem. So we're going to, for part A, let omega sub BA equal E sub B minus E sub A over H bar. And the perturbation, that's going to only couple here. For 1 couples 2, 2 couples 3, there is no direct 1 couple 3 coupling. So our first order transition amplitudes for this, in the interaction picture, that C sub B first order of t equals negative I over H bar, and then that's times the integral from 0 to t, V sub B A, t prime, e to the I omega sub BA t prime dt prime. And since V sub BA of t equals V naught cosine omega t M sub BA, where we have the following here, that M 1, 2 equals M2, 1 equals M2, 3 equals M3, 2 equals 1. Then what we could say here, again, that C sub B first order of t, that's going to equal, I wrote it down here, it's the same thing down here, sorry, I wrote it too compact here. So this C sub B order 1 of t equals negative I V naught M sub BA over H bar integrated from 0 to t cosine of omega t prime e to the I omega sub BA t prime dt prime. And from here, what we're going to do, use cosine omega t prime equals 1/2 quantity e to the I omega t prime plus e to the negative I omega t prime, close parentheses. So C sub B order 1, or C sub B order of 1, first order, C sub B first order of t, sorry about that, equals negative I V naught M sub BA over 2H bar times this quantity, e to the I times omega sub BA plus omega, close parentheses, t minus 1 over I quantity omega sub BA plus omega, then plus e to the I omega sub BA minus omega t minus 1 over I times the quantity omega sub BA minus omega. Building on that for letter A, let's see if this holds up. Let me just take this down. So here for letter A, this applies here for these couplings. So this applies for the allowed transitions here. So we have right here this coupling 1 to 2, and then we have here the 2 couples 3, and for 1 couples 3, C sub 3 first order here of t from 1 equals 0, C sub 1 first order of t from 3 equals 0. So that is part A. Okay, so part B, what they want us to do is determine the resonance conditions for part B. So here for part B, let's see, resonance conditions. Resonance occurs when the denominator becomes small. Omega sub BA minus omega is approximately 0. So H omega is approximately E sub B minus E sub A. Allowed 1 photon resonances are omega is approximately E sub 2 minus E sub 1 over H bar, and omega is approximately E sub 3 minus E sub 2 over H bar. There is no first order resonance for the 1 to 3 coupling there. because V13 equals 0, or 1 couples 3, because V13 equals 0. Okay, building on that, going into letter C, find the transition probabilities between all states. So the transition probabilities for an allowed transition, here we have the following. So that A to B, we have P sub A to B, first order of T, equals absolute value of C sub B, first order of T squared. Near resonance, omega is approximately omega sub BA. The counter-rotating term is rapidly oscillatory, and the dominant term here, C sub B, first order T, is approximately negative I V naught over T 2 H bar times this quantity in the numerator, e to the I, raised to the e to the I times this I times quantity omega sub BA minus omega, close parentheses, T minus 1 divided by I times the quantity omega sub BA minus omega. So from here, we let here delta sub BA equal omega sub BA minus omega. Then we're going to wind up with the following. P sub A to B, first order of T, is approximately V naught squared over H bar squared times sine squared of this delta sub BAT over 2 divided by that delta sub BA squared. And equivalently, this P sub A going to B, first order of T, is approximately the quantity V naught T over 2 H bar squared, 6 squared of delta sub BAT over 2. So our allowed first order probabilities are here for P, 1 to 2, 2 to 1, 2 to 3, 3 to 2. Okay. And our forbidden at first order, P sub 1 to 3 of first order equals 3. P sub 3 to 1 first order equals 0. So this transition, that 1 to 3, what we're going to get may occur through second order perturbation via intermediate state 2. Moving along to part D, they want us to derive the rotating wave approximation. So for part D here, rotating wave approximation, we suppose the drive is near that transition 1, 2, 1 couples 2, and that transition here, omega is approximately omega to 1. So the slowly varying terms are proportional to e to the I omega to 1 minus omega t. The rapidly oscillating counter-rotating terms proportional to e to the I parentheses omega to 1 plus omega t are neglected. Okay, so in this ket 1, ket 2 subspace, the effective interaction picture Hamiltonian is here. This h sub I superscript RWA equals V naught over 2 times this matrix, first row 0, e to the negative I delta t, second row e to the I delta t 0, where delta equals omega to 1 minus omega. So transforming to a frame rotating with the drive gives the time-independent effective Hamiltonian. H sub EFF equals H bar delta over 2 sigma sub C plus V naught over 2 sigma sub X. The Rabi frequency here is omega sub R equals the square root of delta squared plus quantity V naught over H bar squared. And on exact resonance, delta equals 0, so omega sub R equals V naught over H bar. And for letter E, we want to determine the long time behavior when omega equals E sub 2 minus E sub 1 over H bar. So for this long-term behavior for omega equals E sub 2 minus E sub 1 quantity over H bar, here the drive is exactly resonant with this coupling 1, 2. And if the system starts in ket 1, then in RWA, this P 1 to 2 of T equals sine squared of V naught T over 2H bar. So here, P sub 1 to 1 of T equals cosine squared of V naught T over 2H bar. So the state undergoes a Rabi oscillations here. So we have the following here. We have ket psi of T equals cosine V naught T over 2H bar ket 1 minus I sine of V naught T over 2H bar ket 2. So up to the usual Schrodinger picture, phase factors, the level ket 3 is populated only if the same drive is also near. And building on that, same drive also near. Sorry, forgot to add that. My mistake, not enough coffee yet. So let me read this. The level ket 3 is populated only if the same drive is also near resonance with that coupling, the 2 couples 3. Okay, now we're ready to move on to the rest of letter E. So if we have here, if omega 3, 2 does not equal omega, then this 2 couples 3 here transition is off resonant and remains small when the absolute value of W32 minus, when the absolute value of omega 32 minus omega is much greater than V naught over H bar. That's how, and I do that all the time. If I'm going too fast, I conflate omega with W. I do that, I don't know, too many times still after all these years mispronouncing variables. The system exhibits resonant Rabi oscillations between ket 1 and ket 2, while ket 3 is only weakly populated if 2 couples to 3 is off resonance. Okay, so sorry about that. If I mispronounce anything, but thank you very much, and have a great day.